Welcome back to the third installment in our pre-calculus journey through Unit 1. Today's content includes rational expressions. Our vocab for today's activity is a rational expression, domain, and the conjugate radical, which goes hand in hand with the process that we've been applying in the previous two lessons when we are rationalizing a denominator. Our learning objective includes we are learning that the domain of a function is the set of all possible inputs and the range is the set of all possible outputs, so I can operate arithmetically on rational functions. I'll know I've got it when given a description of a function that represents a situation. I'm able to determine a reasonable domain and range. Let's begin. So what is a rational expression? Well, the word rational is a much more older and mature, like yourself, version of the word fraction. It is a fractional expression in which both the numerator and denominator are polynomials. The domain of an algebraic expression is the set of real numbers that the variable is permitted to have. And what we mean by that is you might have come across instances when you are utilizing a calculator where you type in a value and your calculator spits back an ERR or a UND for error or undefined. So I want you to think of some of those instances and try to describe them here. What are some functions that have certain restrictions regarding their domain? Why do these particular functions have restrictions? Okay. Possible functions include a linear function, a quadratic function, an exponential function, a square root function, a rational function. I'm not saying that all of them have restrictions, but those are some that could jumpstart your thought process. Now, at this point of the video, we are going to define what the domain is of the following expressions. For the first function, we call this a polynomial. If we wanted to be a little bit more specific, we could say that it is a quadratic expression. Equations have equal signs. So being that it's a quadratic expression, if I select any value of x, I will always be able to get an output. If I make x 0 and substitute that value in, my output would be 1, right? 2 times 0 is 0, plus 3 times 0 is 0, plus 1 is 1, right? Regardless of the number that I pick, any number would work. So there are a few different ways that we are going to be able to notate our domain. Okay. One of those ways is through interval notation. So if x can be any number, I can literally say from negative infinity, right, my leftmost bound, all the way to positive infinity, my rightmost bound, every number in between those, right, so that's literally every number, is what x can be. Oops, I do not want to do that type of slash. I don't want to do an absolute value sign. So let's say, I guess I'll have to write this next one. We call that interval notation. Set notation is going to look a little different. Right? I can say that x is an element. This is epsilon. It's a Greek letter. Of all real numbers. Okay, so x can feasibly be any value that we can possibly think of. Okay. Based on the previous slide, you should have come to realize that both rational And this is we can't really define this as anything. We could just say it's an expression, but it's a radical and rational. So there's a lot going on, right? With rational functions, we need to look at the denominator, right? Because we are not allowed to divide by 0. So we can say that x I wonder if they have an element button. Let's find out. Let's press the keyboard. Epsilon, epsilon, epsilon. Where are you? Are you here? Paging epsilon. Nope, just capital letters. All right, so what I'm going to do is I'm actually going to use the arrows. Okay, so that's going to, for me, say x is an element of. We'll say that x cannot equal 5. Let me clear that out of the way. Put this back here. And they also have the do not equal sign. All right, so let's do it this way. Say x cannot equal 5. I'm gonna have to probably write this one out. Right, x cannot equal 5 because 5 minus 5 will give us this divide by 0, and that's no good. In addition, square roots are not allowed to take negative values. So that's something that we want to be mindful of, right? So if it can't take negative values and it can't take the specific value of 5, we would want to say that x must be greater than or equal to 0, but x can also not equal. Nope, that don't work either. Don't work either. So we'll do this. X and then a /5. I'll see if I can work through some troubleshooting there. That way we can type out the does not equal to sign. But this component here, saying that x must be positive, but it also cannot equal 5. And we'll work through this again if that was a little choppy because of the tech. So do me a favor and fill out what the domain is for that rational expression. Moving on, we're going to spend some time simplifying rational expressions, right? So this is basically our algebraic version of fractions. Talk to me about what you remember from your experience in Algebra 2. There's a specific pattern or methodology that we can apply, but I want to see how much you are able to recall. Which brings us to here. So I'm going to type everything out so you can see that it is doable. So in our numerator, the expression 2x plus 2 has a common factor of 2 in both terms. I can factor out a 2, and the corresponding expression would become x plus 1. Now the denominator is a little trickier. You have to rely much more on your intuition here than this pre-programmed set of responsibilities. But in the previous video, you might have heard me say, right, that formulaic 2 numbers that multiply to our constant, but add or subtract to our linear term. So conveniently, 5 only has 2 factors, 5 and 1. And if we add them, we get 6. It works out, ironically, It's a textbook problem. So if I wanted to tease apart or factor this expanded form, right, my first expression would be x plus 5, and I would multiply that correspondingly with x plus 1. We can see that since we have the same expression in both the numerator and denominator, and they're being multiplied in both locations, we can simplify those out, and our simplified rational expression would be 2 divided by x plus 5. Erase that. So at this point, we're going to immerse ourselves in all arithmetic operations on rational expressions. Right, so we just simplified. That's not an arithmetic operation, but arithmetic operations include addition, subtraction, multiplication, and last but not least, division. It becomes a little bit more complex here because we have algebraic expressions rather than singular numeric values. However, it is strikingly similar to when you did those operations on numerical fractions. So, to multiply rational expressions, we multiply their numerators and multiply their denominators. Now, a compound fraction is a fraction in which the numerator and the denominator are themselves fractional expressions. That would be the second row of this table, a divided by b. Right, the numerator is a fractional expression. The denominator, c divided by d, is also a fractional expression. So in this case, right, to divide rational expressions, we invert the divisor, means apply its reciprocal, and multiply. Yes, there is a god-awful mnemonic device that people reference. I will not reference it because I don't rely on those things, but you can as well. So adding and subtracting rational expressions is a slightly more complex, I'm missing a word here, process. It requires a least common denominator. And identify the least common denominator for rational expressions by taking the product of each algebraic component, multiplying them accordingly.